How's everybody doing? Hear me okay up there? Do you hear me okay up above? Good. All right. So I usually have a better success rate of scaring people away after the first day, so I guess I may need to work on that. We are moving forward. Today I'm going to spend a fair amount of time talking about solutions, buffers, and may touch a little bit on amino acids and how they can act as buffers as we get going forward. So that's my hope. I left this screen or I left this image on the screen. So for any of you who weren't here on Monday, you can copy the URL down about where you'll get information. And that this class, this page will be where essentially all information in the class comes through. And the syllabus is on there, which is required reading. So all those things are there. I hope everybody got to access the video okay. Any problems with the video? Seeing none? I will assume everything is working okay. So if you have problems or questions or technical difficulties, let me know. I've already seen a few of you, not about technical difficulties, but about questions and so forth. So I'm always happy to meet with you. And please don't be a stranger. So I'm happy to connect with you in that way. Okay. Let's turn our attention to thinking more about acids, bases, and buffers. And why is that way over there? Oh, come on. Okay. Okay. And get rid of that. And get rid of that. And get rid down here. Okay. Have to arrange things. All right. So last time I talked about, obviously, what's involved in aqueous solutions. In the recitations, the TAs are taking you through and leading you through some of that, leading you through some calculations, and so on and so forth. Excuse me. It's important for you to understand what's going on with those. Okay? And like I said, this is freshman chemistry that a lot of people didn't, they thought they were never going to see it again. And one of the things about education is you never really escape anything ever. So it always comes back. So that's why it's important to learn it when you can. Because the next time you see it, it comes back up in a better way. Okay? So anyway, getting back to what I was talking about last time, I had just started talking about acetic acid. And acetic acid is an example of an acid that I'm going to show a lot of this term. So I want to repeat a little bit of what I said last time and get you thinking about what I described last time as a practical way of doing chemistry. Practical chemistry, practical calculations mean that you understand what's happening, and what's happening is much more important than the numbers that you otherwise have been trained to crunch. Okay? I get students that crunch numbers really well, and they make a slight mistake, and they get a number that doesn't make any sense at all, and they don't realize that. So understanding it from a practical sense will tell you if what you thought you calculated is correct or not. Okay. Well, I said last time that in this class, I'm going to use a couple definitions that hopefully simplify things for you. I described, first of all, an acid was something that had a proton to donate, and a salt was something that was an acid that had lost a proton. Very simple things. I didn't use the term base, and I said in the class, I'm not going to use the term base, okay, except when we talk about a strong base. Only when we talk about something that completely ionizes. Okay? Well, do we use the term strong acid? And the answer is we do. So in this class, we'll have strong acids, we'll have strong bases, we will have acids, and we will have salts. Do we understand? When I say acids, I'm talking about, in general, a weak acid. Acetic acid is a weak acid. Right? Acetic acid is a weak acid. So what does it mean to say something is a weak acid? Right? Well, let's start with what you learned in freshman chemistry about what it means to say something is a strong acid. Right? A strong acid is something that completely dissociates when you put it in water. When you put a strong acid in water, it completely comes apart. I gave you an example of a strong base. I said you put sodium hydroxide in water, you put 100 million sodium hydroxides in water, you end up with 100 million sodiums, and you end up with 100 million hydroxides, and it's completely come apart. It's no longer sodium hydroxide, it's sodium and hydroxide. They come apart. Na plus, OH minus. Well, if we extend that logic to strong acids, we come up with exactly the same thing, except instead of having strong base, we have a strong acid. If we take HCl, the most common acid that you study in freshman chemistry, if we put 100 million HCl's into a solution of water, we will end up with 100 million protons and 100 million chloride ions. It will no longer exist as HCl. It will be H plus and Cl minus. Okay? Now that's important to remember. So, anytime I put HCl into a solution, or anytime I put NaOH into a solution, it will completely come apart. Now what you learned in freshman chemistry was, well, if you have a solution that's 10 to the minus fifth molar HCl, what's the pH? Without even thinking about it, you said, okay, well, 10 to the minus fifth, negative log of 10 to the minus fifth gives me 5, so the pH is 5. Okay? And you didn't think, well, that HCl had to come apart. And when it came apart, it gave 10 to the minus fifth molar protons. And 10 to the minus fifth molar protons gives me a pH of 5, because it's the negative log of the 10 to the minus fifth molar protons. Okay? You didn't think about that, right? It's important to think. It's important to think about that. Okay? You need to keep those things in mind. And you need to keep those things in mind because weak acids don't behave that way. Weak acids don't behave that way. Weak acids don't come completely apart. If you simply take acetic acid, HAC, and you put it into water, as I said, you can put 100 million in there, and you're going to get a few thousand that are going to come apart. It's a weak acid because it doesn't give very many protons when you dump it into water. Now, one of the things you're going to see with weak acids that's really interesting and really important for us as living beings who rely upon them is that weak acids are at the root of our stability. They're at the root of our stability. Weak acids, as we will see, have the ability to absorb protons or donate protons. They have the ability to do both. And because of that, weak acids help resist changes in proton concentration in a solution. I'm going to repeat that. That's a very important point. Weak acids have the ability to resist the change in proton concentration in a solution. Well, since we said proton concentration is measured by pH, if I extend that logic, then what I'm saying is that a weak acid has the ability to resist a change in pH, because proton concentration is related to pH. So therefore, a weak acid has the ability to resist a change in pH. Now that turns out, as I said, to be an immense and essential stabilizing factor for us as living beings. Why? Well, we'll see why when we talk later about proteins, but I'll give you an insight quickly. Okay? I told you how protein shape was essential for protein function. Protein shape is related to the pH of the solution in which the protein is found. If we change the pH, we change the shape. If we change the shape, we change the function. And we have a very good way of losing function of a protein if we change the pH too drastically. If I take HCl and I've got a solution of bacteria here and I dump HCl into that solution, I dump enough HCl in there, I'm going to kill the bacteria. Because all the proteins are going to not have the right shape. And since proteins are essential for that bacterium to be alive, or those bacteria to be alive, those are going to die. Okay? All right. Well, how is it then that a weak acid is able to do this magical thing? Okay? Well, first of all, let me tell you a word I've just defined for you without even giving you the definition. A weak acid can act as a buffer. You've heard the term buffer before. Now I'm going to give you the definition. I already gave it to you. A buffer is something that has the ability to resist a change in pH. A buffer is something that has the ability to resist a change in pH. What does it mean to say resist a change in pH? Okay. What does that mean? Well, it means that if I have a buffer under the right conditions and I add some protons to that solution that has the buffer, the pH won't change very much. That's what it means. So if I alter the proton concentration in that solution by adding something to it, I will not see the pH change very much. Now, a lot of you are sitting here going, oh, I've learned all this in freshman chemistry. And a lot of you are going to forget that when we get to working buffer problems. Right? Very important to remember. I'm going to show you how it is that a buffer resists a change in pH. Okay? You have to take it for granted from me at first that a buffer can resist a change in pH, meaning that it can resist changing its pH when I add more protons or take protons away from a solution in which a buffer exists. Okay? Well, how do we do that? Okay? Well, let's go back to our equation looking at the dissociation of acetic acid. There's the dissociation of acetic acid. There's the dissociation of acetic acid. All right? That's what happens if I put it in water. I say it doesn't happen to a very big extent. Okay? But we're going to see that we can alter that extent a lot. We can alter that extent a lot. How do we alter that extent? Well, let's look at what's going on. Whenever you're working a buffer problem, I want you to think about this very thing I've just written on the screen. Okay? If you want to call it a general acid instead of an acetic acid, you can just call it HA and proton plus A minus. That way it can be any acid, where A is the salt of any acid. Okay? What happens in this? Well, if I do nothing else, this equation isn't going to happen very much. I'm not going to see this go very far. That's what's going to happen. And I'll get a little bit of H plus, and I'll get a little bit of AC minus, but I won't get much of anything else. Well, what if I do this and I start taking away protons? I have some acetic acid, I put it into a solution, and then I start taking away protons. What's going to happen? Well, taking away protons is actually fairly easy to do. You learned it in freshman chemistry, but if I asked any of you right now how you take away protons, I would wager that probably 2/3 of you wouldn't be able to tell me. So I'm going to tell you. It's not a pop quiz. Okay? You take away protons by adding hydroxide. Because when you add hydroxide, OH minus combines with H plus and makes water. You guys did titration plots in freshman chemistry? You did something like what I did. You put a drop in, you measure the pH. Put another drop, you measure the pH. Put another drop, you measure the pH. You kept doing that ad nauseum. There was a certain range where you kept adding a drop and you didn't see much of a change in pH. And you thought this experiment's never going to end. Okay? And you thought it was never going to end because what you were learning was you were in the region where the buffer was working. Adding more things that take away protons isn't changing the pH very much. That's what a buffer's doing. Okay? If we look at it graphically, it looks like this. Okay? We start with a solution. Here, notice we're plotting pH on the y-axis. We're plotting OH added on the x-axis. And by the way, when you draw a graph in this class, it will only be right if the axes are properly labeled. A graph with a shape on it that has no axis information is not a graph, because the shape depends upon what the axes are. Okay? Remember that. All right. So I've got a solution here that's of a weak acid. And its weak acid, I started with a very low pH. I put it into solution, and that solution had a pH of, let's say, 0. If I have a solution that's a pH of 0, tell me what happens. Tell me what the concentration of protons is, high or low? high, right? There's a lot of protons in there if that pH is 0. All right? That's where my titration plot started. A ton of protons in there. Right? I start removing protons by adding hydroxide. How would I add hydroxide? Well, I would add a strong base, sodium hydroxide. That sodium hydroxide would add, and if I added, let's say, 100 million sodium hydroxides, how many hydroxides am I going to get? 100 million hydroxides, right? For every molecule of a strong acid I add, excuse me, I will make one hydroxide because it completely comes apart. I start adding hydroxide, and what happens to the pH? You say, well, duh. If you add hydroxide, you start taking away protons, the proton concentration is going to go up. And what do we see? The proton concentration starts going up. It's going up. Okay? Well, then something magical happens. All right? And the something magical that happens is it goes up, but then we see that the more protons we add, it gets to a point where it starts flattening out. That was that freshman chemistry experiment where you added a drop and very little happened to the pH. And you're bored. You're probably bored right now too, right? Excuse me. Okay? It's flattening out. Why is it flattening out? Okay? To show you why it's flattening out, we have to go back and think about this equation. Okay? Why is it flattening out? This is the equation I want you to write down to remind yourself what's happening in a buffer anytime you're working a buffer problem. I just started with a solution that had a ton of protons in it. What's that sign there mean? What does that mean? Reaction goes both ways. It means equilibrium. Equilibrium means things can go both ways. All right? Le Chatelier taught us a principle in chemistry. What was the principle of Le Chatelier? Anybody? So a system responds, okay, to change to try to reestablish equilibrium. That's what Le Chatelier's principle basically says. If I try to move things one way, and you're right, by taking away products, then the reaction will move forwards. And if I take away reactants, the reaction will move backwards. Right? I started with a solution that had a ton of protons. Okay? I had a ton of protons right there. Which direction is this equation favored, to the left or to the right? It's favored to the left because all these excess products are going to drive the reaction back this way. When I started with that solution at a pH of 0, I had a ton of protons, and those protons combined with AC minus to make an HAC. Almost everything, when I started that solution, was in the HAC form. Then I started adding my sodium hydroxide. And as I started adding that sodium hydroxide, I added hydroxides. And what do hydroxides do? They combine with protons. And so what happens to the proton concentration is I start adding hydroxide. The proton concentration goes down. And when I start pulling things away from the right side of this equation, what happens to this equation? It starts moving to the right. If I take away product, the equation's going to move to the right. Well, let's think about this. I've started moving to the right. What happens to my concentration of HAC? It's going to decrease. Because what's my source of protons? HAC. The only place I can get protons is from the weak acid. So if I start taking away protons, what's HAC going to do? It's going to start releasing protons to make up what I started taking away. Okay? HAC concentration is going to go down. What's going to happen to the AC minus concentration? It's going to increase. Why is it going to increase? Because when I take an HAC and I pull a proton off of it, what do I get? AC minus, right? So you see I've started manipulating this equation by adding hydroxide. Let's take a theoretical situation. Theoretical situation is I start with 100 million HACs. That's what I started with. Let's say I start with 100 million HACs, nothing else. Now I just added 10 million hydroxide ions. 10 million hydroxide ions. There's going to be a few protons floating around because water has protons in it, right? Not very many, but there's going to be a few protons in there. So as I start gobbling up those protons with the hydroxides that I add, what's going to happen to those few protons that were in there to begin with? Well, HAC is going to try to replace them, right? How many is it going to try to replace? 10 million. I added 10 million hydroxides. I'm going to pull out 10 million protons. And what's going to happen? I'm going to lose 10 million HACs. You can do the math. How much will I have left? 90 million. And how many AC minuses am I going to have? I'm going to have 10 million. Right? Now, I knew how much I added. I therefore know how much AC minus I have, and I know how much AC I have left. Does that make sense? If that doesn't make sense, you're going to have buffer problems. That is, problems doing buffer problems. Problems with problems, right? If it doesn't make sense, come see me. Come talk to me, all right? We can manipulate that. Well, let's say, okay, all right, so we've added 10 million hydroxides. We've now pulled this over here. Do I know how many protons I have in that solution? I don't. I didn't know how many I started with. I knew water had some, but I didn't know how many I started with. I don't know how many protons are in that solution. Right? But I can calculate that. How do I calculate that? Well, it turns out that there's an equation called the Henderson-Hasselbalch equation. It's right here. The Henderson-Hasselbalch equation allows me to determine how many protons are there. It allows me to do that. This equation, which you're going to see a lot of, and which the TAs have been working through in class and will continue to work through in class for the next week or two, says that there's a relationship between the pH and something called the pKa, which I'll describe in a minute, and the ratio of salt to acid. Okay? pKa is a constant. Okay, so it's just a number. pKa is a constant for a given acid. I'm going to say more about it in a minute. We're not going to worry about that for the moment. We're going to think about the relationship between the pH and the ratio of salt to acid. Okay? Now, the pH is here. The ratio of salt to acid is here. What happens if the ratio of salt to acid increases? What happens to the pH? Okay? So, as the ratio of salt to acid increases, the pH is going to increase because pH is related to that. This is just a number, 5. pH equals 5 plus this. If this number gets bigger, this number will get bigger. That's a practical way of looking at this. It didn't involve punching anything into a calculator. It told me that as the ratio of salt to acid increased, that is, as I had more and more salt, the pH is going to go higher. Right? Make sense? Don't say yes if it doesn't. At this point, I should be seeing some people doing this, but nobody's doing this because I don't want to be seen doing this. He's going to pick on me if I do that. All right? I'm going to remind you, I just told you that as the ratio of salt to acid increased, the pH was going to increase. Let's go back to our equation, or our plot. What happened when I added hydroxide? pH increased. It's the most common answer I get. But what happened in that solution? I told you earlier what happened. So protons got taken away. What did that mean? Salt increased, right? What happened to HAC? It decreased, right? Didn't the salt to acid ratio increase? What did I say happened when the salt to acid ratio increased? And what happened to the pH? You guys know I don't lie to you. I tell you the truth. Okay? All right, so we see the pH goes up as the ratio of salt to acid increases. All right? Now, let's imagine we go back to our equation and we say, all right, here's our Henderson-Ossaback. And by the way, that's a dash. That's not a minus sign. That is a dash. Okay? All right? Let's imagine, if you will, that we, instead of adding 10 million hydroxide or sodium hydroxides to that mixture of 100 million HACs, instead of adding 10 million, let's say we add 50 million. Well, you can do the math. How much HAC, how many AC minuses am I going to have? 50 million. How many HACs am I going to have? 50 million. Oh, wow, Kevin picked a cool number. The two are equal, right? Well, I picked this number for a reason. What is the ratio of 50 million to 50 million? It's 1. And what is the log of 1? 0. I've just picked a situation where I have equal amounts of salt and acid, and the log term becomes 0. What does that mean? It means pH equals pKa. I've just given you a definition for pKa. There are a couple. One of them is that the pKa for a weak acid is the pH at which salt equals acid. It's a practical thing. We haven't pulled out a calculator yet. The pKa is the pH at which salt equals acid for a weak acid. Okay? You with me? Okay, bear with me. This won't be too painful. Won't always be painful. Okay? We've just found what pKa is. Now, let's go back and look at our buffer plot. You notice I had marked that little thing right there, and I said that's the pKa. If I showed you that plot and I said, what is this point? It's the pKa. What would you tell me about that buffer solution? Well, I hope you would tell me that salt equals acid. Right? At this point, the concentration of salt and acid are equal. Okay? Now, the pKa also turns out to tell us some other things. The pKa tells us the strength of a weak acid. It's a constant for a given acid. So acetic acid has a pKa of 4.76. And by the way, you won't have to memorize that. And by the way, you won't have to memorize any equation on the exam. I will give you every equation you need to know. It's a pretty good deal. All right? No memorizing of equations. I'm going to give you every equation you need on the exam. All right? Okay. So the pKa is a measure of the strength of a weak acid. We saw that as the pH went down, the proton concentration went up. You will see as the pKa goes down, the strength of a weak acid goes up. Okay? The strength of a weak acid goes up as the pKa goes down. So if I compare two weak acids, let's say I have acetic acid. It has a pKa of 4.76, and I compare it to formic acid, which has a pKa of 3.75. Which one is the stronger acid? Well, duh. Formic acid has a lower pKa. Formic acid will be the stronger acid of the two. Everybody with me? Okay. Now, let's think about what this graph is telling us. All right? Right here, we said that salt and acid were equal, right? Let's say that I wanted to change this solution so that I had more acid than salt. What would I have to do to it? I started with an equal, and now I want to have more acid than salt. What am I going to have to do? What's that? Okay, removing OH, yes, but there's a better way of saying it. What would I have to do? Increase the concentration of protons. And how will I increase the concentration of protons? Adding a strong acid. So if I add HCl, I'm going to see it go this way. If I add NaOH, I'm going to see it go this way. If I looked at this graph and I said, okay, at this point on this graph right here, is there more salt or is there more acid? What would you tell me? More salt. Okay? If I asked you down here, you would say, well, there's more acid. If you're not sure about that, come see me. Or if you're not sure, ask me a question right here. Okay? That's what's happening in this solution. I can manipulate this by adding things. Now, let's get back to the part about the buffer. I said a buffer was something that resisted change in pH. Look what's happening. In a certain region of this, it goes up very rapidly. It goes up rapidly here, and it goes up rapidly over here. But in this region from here to here, it doesn't go up very rapidly. That region is known as the buffering region, because it's in this region that when I start altering the concentration of protons, the pH doesn't change very much, from about here to about over here. We will say that the buffering region for an acid is plus or minus one value of the pKa. Plus or minus one value of the pKa. Okay? So for acetic acid, if I have a weak acid which has a pKa of 4.76, which is what acetic acid has, the buffering region for acetic acid will be between 3.76 and 5.76. And if I'm in that region, I will not see the pH change very much. About 3.7, this is a different acid, but from about 1 below to about 1 above, I will not see a change, a significant change in the pH. Why does that happen? Well, it actually happens because of that log term. That log term is what flattens this thing out. In that region where we're near a value of 1, it's very flat. Okay? Well, I'm going to give you another practical thing to think about. Okay? pH equals pKa plus log of salt over acid. Let's say I've got a solution of acetic acid, and it's at a pH of 7. Do I have more salt, or do I have more acid? I hear more salt. Do I hear more acid? It's unanimous. It's rare you get unanimity, or I just get a class that's afraid to disagree. Okay? I have more salt. How would I know that? Well, I say, well, you just showed us on the graph. Well, what if I didn't show you a graph? How would you know that? What if I said I have an unknown acid that has a pKa value of 5.1, and it's in a pH of 3, what would you say about salt and acid? More acid. Okay. Now, what you're doing very quickly is you're just saying, well, I know the rule, all right? It's better to know what's happening than to know the rule. What's happening? Here's what's happening right here. Your answers are always going to be rooted in your Henderson-Hasselbalch. Let's think about this. I've got a pH of 3. I've got a pKa of 5.1. pH is lower than the pKa. What does that mean about this number over here? It means that this number has got to be negative. And how do I make a log term negative? A log term is negative when its ratio is less than 1. And to make this less than 1, what do I have to have? More acid than salt. Now, we haven't touched a calculator. You're not going to use a calculator on the exam. You're not going to get to. And I don't do that to be mean. I actually do this to save your necks. Because it's much more likely you're going to make an error punching something into a calculator than it is you're going to understand the logic of doing something that I just described to you. Okay? That means that I can't ask you to go and crunch numbers and say, well, here's this, what's the pH? Because you don't know necessarily how to calculate that log term. But you should be able to figure out. I have to give you problems that you can figure out. And that's what I will give you. Let's say that I had twice as much acid as I had salt for a weak acid. Twice as much acid as I had salt. Is the pH of that solution higher or lower than the pKa? I hear unanimity. I think you guys, everybody learns this. Everybody knows this. I know everybody doesn't know this. There's some people going, God, I don't know what the hell he's talking about. But I'm not going to raise my hand. He shoots people that raise their hand. This guy's evil. Okay? All right? But you're exactly right. Because if this is twice as much as this value is 1/2. And the log of a number less than 1 is negative. If this is negative and this is positive, that means this has got to be less than the pKa. Figured it out. No calculator. Okay? Now, I'm going through kind of fast. I'm going to slow down and take some questions. Questions. What do you not understand about what I've just told you? What would you like to know more about? You're sitting there stunned. I should have a taser. I wouldn't have people looking so stunned. Yes? Oh, good question. So is the pKa of a strong acid essentially 0? For the purpose of this class, we will say that a strong acid does not have a pKa because it completely comes apart. If it completely comes apart, what's the ratio of salt to acid? It's 0. Well, actually, no, I take it back. It's actually infinity, right? It's 100 million divided by 0, and we can't take the log of infinity, right? So a strong acid in our scheme cannot have a pKa. If you see a problem where there's a pKa, it's a very good question. If you see a problem where a pKa is listed for something, the first thing that pops into your mind, besides the fact Kevin has a frog in his throat, the first thing that should pop into your mind is, he's giving us a weak acid. Because if it has a pKa, it is a weak acid. Make sense? All right. Now, there are a variety of problems that I've put onto the sheet that I want you to look through. You're going to work in your recitation. Your TAs are going to work with those. You're going to work with those. I'm happy to help you. Your TAs are happy to help you. I haven't posted their office hours yet, but I will be posting those soon, and you'll have those. Other questions about what I've been talking about? Because if not, I'm going to move forward. If you really want me to slow down, you'll ask me some questions. Yes. Oh, way back in the back. Yes. Yeah, no calculator dealio. Okay. You are not going to need one because I'm not going to give you anything that's going to require a calculator. So the answer to your question is, am I going to give you even numbers? I'm going to give you something that's not going to require a calculator. Yes. Okay? It's not going to require a calculator. You're not going to calculate any logarithms. You're not going to do any of that. But you may have to tell me, is the pH higher or lower than the pKa? You may have to tell me, do I have a greater amount of acid or salt, excuse me, based on what I've told you, right? If the pH is 5 and the pKa is 2, more acid, more salt. pH is 5, pKa is 2. More salt, right? Greater than that means it's got to be a positive number. If this is a positive number, what does that mean? Ratio's got to be greater than 1. Got to have more salt than I do acid. Okay? So that's the kind of problem that we're talking about. You're not going to crunch numbers on any of my exams. Yes? How do we know that this equation is true? Okay? A reasonable question. One of the reasons that you did the titration plot back in freshman chemistry was to actually answer your question you just asked. If you do that, you'll see that you can plot a theoretical plot, and you can see that the actual plot will mirror it. Okay? Very good question. I like this, by the way. You should always doubt. Well, how in the hell do we know it's true? Just because you say it's true, Ahern, how do we know it's true? You know, I'm not God. It's important to think about these things. Very good. Okay. Well, as many of you know, I like to do songs, so I thought this might be a good point for us to do a song before we move on to the next stuff. How's that? Okay? The rule in this class is, if you haven't heard my songs before, we're going to sing them, all right? If you guys sing loudly, then I will ensure that we have an extra credit question on the next exam. On the other hand, if I have a hard time hearing you over me, then there won't be any extra credit question. Deal? Deal. And no, you can't have my microphone. All right. So here's a song I wrote for beginning biochemistry students. It's called Biochemistry, Biochemistry, to the tune of Oh Christmas Tree. Please join me. Biochemistry, biochemistry, I wish that I were wiser. I feel I'm in way o'er my head. I need a new advisor. My courses really shouldn't be such metabolic misery. Biochemistry, biochemistry, I wish that I were wiser. Biochemistry, biochemistry, reactions make me shiver. They're in my heart and in my lungs. They're even in my liver. I promise I would not complain if I could store them in my brain. Biochemistry, biochemistry, I wish that I were wiser. Biochemistry, biochemistry, I'm truly in a panic. The mechanisms murder me. I should have learned organic. For all I have to memorize, I ought to win the Nobel Prize. Biochemistry, biochemistry, I wish that I were wiser. Excellent. All right. You're well on your way. Yes, thank you. You're well on your way to an extra credit question on the first exam, so that's good. All right. Okay. Actually, there's one other thing I meant to show earlier, and I'll do that right now since it's also a breaking point. If you click on the YouTube videos, I wanted to show everybody this because it's a trick that's really helpful. If you click on the YouTube videos, you'll go to the link that has the YouTube videos. And I find that most people just simply watch the YouTube video as it exists right there. And that's the worst way to do it. Okay? So if you want to see the laser pointer and you want to see the detail that's in there, there's two things that you need to do. The first is click on this little wheel right here. This little wheel, okay, allows you to adjust the quality. The quality, if I click on that, take it all the way up. I do these at the highest quality that YouTube allows. If you leave this at the low one, you're not going to see stuff. You click on this, you take it to the highest quality, all right? That's one step. And the other step is blow it up to the whole screen. If you do both of those things, you will see this in the same detail that you saw it in here. Your screen will show you all the stuff that I have there. So make sure you do both of those things when you go to watch a YouTube video, and you will find the quality of the video will be immensely better than what you've been used to. Okay? Okay. All right. Let's get out of that and turn our attention back to finishing up here. So we've got about 5 minutes to finish up what I want to talk about. Okay? All right. Well, we care about this not about what buffers are. We care about this not because I give this as problems to torture undergraduates. We care about buffers because they're essential for us to be alive. Buffers allow us, they allow our body, they allow our cells to control pH. That's important because, as we're going to see, our cells and our body are very, very capable of making a lot of protons. Very capable. When you take off and you exercise, one of the things that your cells are doing is making a bundle of protons. And if something isn't absorbing those protons, like a buffer, and resisting that change in pH, then what's going to happen is you're going to have a very acidic solution, and you're going to die. Yeah, okay? That's how critical it is. Okay? So when you thought, well, Ahern just given us problems to work at, now you're sitting there going, man, this is a life and death situation. This is something I need to know, right? I got to know this. That's why, so when people tell you, oh, you're working buffer problems, you say, no, no, I'm dealing with a life and death situation. So, and they're going to look at you as weird as you guys looked at me when I first said that too, right? So, yeah, okay. They've been taken over by the Force. You know? This is how zombie apocalypse is here. You know? This is the buffer apocalypse. You guys have said, I've seen the light. Right? Okay. let's think about, and I'm jumping ahead, but let's think about amino acids. Okay? Amino acids. I'm going to show you an amino acid, and I'm going to show you what happens with an amino acid, and I hope that you're going to recognize something that you've just seen. I showed you acetic acid, and if I said we're plotting pH versus hydroxide added, and we have a weak acid, you would say, oh, well, I can envision that. The pH goes up until we get in the buffering region. It kind of flattens out until we get out of the buffering region, then it goes back up again, right? Everybody remembers that? What if we had a molecule that had not just one proton it could give up, but instead it had two protons it could give up, and both of them were part of a weak acid? That's what an amino acid is. Amino acids have at least two protons that they can donate, and both of them are weak acids. Some amino acids have three. Well, let's think about what that would look like before we actually do it. If I have two different groups that can come off, and each one has its own pKa, do you think that the plot would look different or the same as acetic acid? It would look different. When we thought of acetic acid, where was the plot the flattest? At the pKa value, right? By the way, at the pKa value, the buffer is what we call the strongest. The buffer is the strongest at the pKa value. Well, now I've got two pKa values. I don't think it's too much of a leap in logic to say, hey, in this case I've got 3. What does that plot look like? Okay? Here's what a plot looks like that has 3. We see a flattened region for pKa1. We see a flattened region for pKa2. And we see a flattened region for pKa3. In fact, we could have 10. And every time we got to a pKa value, we would have a flattened region because it's resisting a change in pH at that point. Does that make sense? All right, so we're actually thinking of next lecture. You guys are already moving ahead of everybody else. This is great. Okay, thank you so much for your attention. I will see you on Friday.